So yeah, last time I tried to give you a little sketch about why, with just one extra conserved charge of higher spin, why in more than 2 dimensions actually would kill the whole story, make things trivial, but in 2 dimensions, because you can't, if 2 lines cross, then when you shift them around, they still keep crossing. Although we can rule out nasty, complicated S matrix elements, we do have a non-trivial story left to tell, and it all boils down to the 2-particle S matrix. And I just, well, probably if you didn't quite, I think I went through a little quickly the general argument, but I'll just say it again very quickly. The basic idea that Park had was to say that we can shift these lines. So if we act on, so we think of this as a picture of space-time. It is a space-time picture of the scattering process. So we're looking at it, sort of looking at the universe from above. And our 2 particles are coming in along a certain pair of trajectories because we've made them as little smeared wave functions. And then something bad happens, they collide, we can't really analyse that. But after a while, we expect them to separate again into a bunch of trajectories diverging off to infinity again. Okay? And what we've said is we can act on that by sort of this generator, this e to the I alpha q, and its inverse sort of before the interaction. But because that's conserved, we can move sort of part of that generator, part of it. So we act with it in its inverse here. That obviously does nothing. We can move it through the interaction. It doesn't, q is conserved. It doesn't depend on time. And then we'll have rearranged all these trajectories. And the amount that we shift the trajectories will depend on their slope, okay, which is basically the rapidity involved. And the claim is that when you do that, you can cook it, since you can see that at least for one direction of alpha, you can move things in such a way that the fastest particle ends up a long way to the right. Okay? It ends up so far to the right that if I traced its trajectory back, it would only intersect with these 2, the trajectories of these 2 particles, at a moment in time before the time that they knew about each other. Okay? Time is going upwards. Okay? So these 2 particles, we expect to propagate like free particles until they bump into each other. Right? It's a local theory, it's a causal theory, so nothing happens, so effects happen after causes. And the first time we get a cause is when these 2 collide. Okay? And if this intersection point is before then, that's an impossible process. Okay? That can't happen. That would have meant something would have happened before anybody knew to do anything. So this amplitude must be 0, and therefore we deduce that the initial amplitude is also 0. So that's the basis of Park's argument, and then we got all those nice consequences from it. Basically, the set of outgoing momentum had to be the same as the set of ingoing momentum. And in fact, even more than that, the values of these conserved charges on the outgoing particles have to be the same as the set of values on the incoming particles. Right, and we got factorization. So all we need to do now to compute the full S matrix of the theory for any number of particles coming in at any velocity is to find the 2-particle S matrix. Okay, so now we want to get down to something concrete. We actually want to have a function. And that's the aim. And of course, the nice thing about this whole game is that we can get exact answers for this. And if, for example, it was a theory based on the Lagrangian, like the Sypersymmetric theory we talked about at the beginning, or the total theories, we can even then check by doing some perturbation theory, and check, first of all, that what we've guessed is correct, and also maybe do some little testing about whether we're doing perturbation theory in the cleverest possible way, whether perturbation theory really works to give us the right answer for a case where we actually know what the right answer should be, and so on. And we can go ahead and do these things like thermodynamic beta ansatz and so on to find other properties of the theory. So it really gives us a toehold. So, our key object is depending only on the difference of the 2 rapidities, and I can illustrate it by I hope I've got my indices and everything consistent. But anyway, there's a version of it. And we can renotate this in this handy Zamolodchikov-Fadeev algebra picture by saying we've got a couple of symbols. That's an AI and an AJ, theta 2, and if we swap their order, okay, and actually for the moment we ought to have that theta 1 is bigger than theta 2, so we're talking about in state on the left and an out state on the right. And there's a sort of implicit sum on K and L here to take into account the possibility that we might have different particles here which are consistent with all the conservation laws, as might happen, say, for sign normal theory. Okay, so now we need to basically find, so if there are particles, particle types, we need to find, well, r to the fourth functions, okay, of theta. But of course there are lots of constraints. So for example, so first of all, Sijkl equals 0 if AI and AK, or so I and K, or AJ and AL disagree on any QS value. Okay, I think my S was downstairs with the QS. Okay. Okay, otherwise we can sort of shift things around by different amounts and spoil the picture. Okay. And we also have, say, parity, charge conjugation, time reversal invariants. Well, we'll assume it for now. So we have things like Sijkl is equal to Sjilk and a bunch of similar relations. So for example, if we put a bar, if we have some notion of taking antiparticles, putting a bar above each line, and also Sijkl is equal to Si bar, J bar, K bar, L bar, and so on. Okay.
Sorry, it's probably 1. So equal S equal to 0 or 1?
0. If they disagree, okay, so then there's no amplitude, okay, that component is going to be 0. So if I want to go from 2 particles of type 1 to 2 particles of type 2, the amplitude will vanish. Okay, it didn't kind of arise for the side-scroll, for example, it only had one sort of particle. But if it had more sorts of particles, then that's the situation. Okay, yeah. Okay, it would be one of my forbidden amplitudes. Okay, so it would be in the same. It would be in the same set of things as my, say, 2 to 3 or 2 to 4 amplitudes, because I can move things around in different ways. Right. So a little word about the analytic properties. I'm going to have to skip this rather quickly. So what you usually use for 2 to 2 scattering in general, there's a nice way to parameterize things using things called Mandelstam variables. Essentially, we know that everything is relativistically invariant. So if you've just got these sort of 2 incoming and 2 outgoing momenta, you've sort of got lots of stuff going on which actually is irrelevant. It's just sort of the relative orientation of things. So you want to get a set of variables that things depend on less non-trivially. So you introduce something called S, which is P1 plus P2 squared. So these are 2 momenta here, or in general 4 momenta or whatever. So these are introduced. T would be P1 minus P3 squared, and U is P1 minus P4 squared. So when people were trying to analyse analytic S matrices in higher dimensions, they had to worry about all 3 of these at once and deal with functions of more than one variable. Well, actually, there's a general relation, which is that S plus T plus U has to be the sum from 1 to 4 of A, 1 to 4 MA squared. Okay. But you've still got two complex variables to worry about.
So, sorry, the notation P1 and P2 are incoming?
Yes, P1 and P2 are the incoming ones. Sorry, yes, I should have said I and J probably best. Yes, so that's P1, P2, and with some permutation, these are going to be P3 and P4. Maybe the other way around, I won't worry about that.
But they are outgoing. 1 and 2 incoming?
That's correct, yes. So in particular, the one I'll focus on, so in fact, in 1 plus 1 dimensions, only one of them is independent. Okay? Because kind of you can't twist the picture around. Okay, so in 1 plus 1, only one is independent, and we'll pick S. Okay, and in terms of my rapidity variable, S is just mi squared plus nj squared plus 2 mi nj cos of theta 1, 2, where theta 1, 2 is theta 1 minus theta 2. Okay? So S is basically the amount of momentum forward, what you call forward channel momentum. Okay? So if we, in particular, if we had a propagator, so say we had a Feynman diagram like that, then S would be exactly the p squared that's going forward in that propagator. Okay, so that would be 1 over p squared minus m squared plus I epsilon is just 1 over s minus m squared. Okay, that's in quotes, because if you've got more than one mass, then of course it would just be, okay, well, that's the m squared of the internal particle and so on. Okay? So that's a good one to focus on. And then for physical processes, S must be real. It must be larger than or equal to mi plus mj squared, because theta 1, 2 must be real. Okay, if you think about it, and so therefore S is bigger than the smallest values come when theta 1, 2 is equal to 0, and then it's equal to mi plus mj squared. Okay, but we think about this, the sort of clever way to do this is to think about everything in the whole complex plane. So think about everything as functions of a complex variable, a little bit like we were doing before. And then the S-plane, so the complex S-plane, so what we're trying to do is think about all of our amplitudes as sort of, well, analytic functions on a possibly cut complex plane. And it turns out that, so this is S, and we're going to have to scoot rather fast through this, but it turns out that the analytic structure in general of amplitudes on that plane has a pair of square root branch points, so that's a square root and that's a square root. And this is then a branch cut, and this is another branch cut. So it looks a bit of a mess. And this is the point mi plus mj squared, and this actually is mi minus mj squared. Okay? And so physical processes happen actually on the top. So let's say on, let's call it C, where C is the top of that branch cut. Okay? So you can consider continuing amplitudes sort of all the way. You can continue it down through the cut, all the rest of it. Okay? You'd expect to find perhaps, so poles corresponding to these sorts of Feynman diagrams generally hit bound state. Poles generally sit in between these two branch points. Okay? If it was possible to produce a physical particle as a bound state, which of course would be bad news because then that particle would be unstable, it would sit somewhere along here. In general, what happens is if there are unstable particles, they sort of hide just below this branch cut and give you these sort of resonance peaks and scattering amplitudes and so on. Okay, well that's the general picture.
But this assumes that you have only two particles.
This is the sheet for this particular amplitude. Okay, so if we have other particles, then there'll be sheets for those particles as well. Okay, there'll be an S variable for those other particles. I'm talking about this particular component at the moment. Okay? The function.
So it was good if you can produce something else than just particles in the final state. For instance, 3 particles. It's a non-integrable theory.
Yes, okay, good. So yes, if I have a non-integrable theory, so this is the initial picture. If it was non-integrable, then I'd have, well, there'd be these moments. So in fact, this, I shouldn't say thanks for asking, because that kind of sounds like a politician who really wished that he hadn't been asked the question. It's genuine. So this is actually sometimes referred to as the 2-particle threshold, because this means that the S channel has enough energy just to have 2 particles travelling with 0 relative momentum in it. Okay? And of course, for all physical processes, you already have that much energy in your in state. Okay? So at this point is where physical processes start. But as you move along here, along C, you're getting more and more energy sort of travelling forward. Okay? So, and actually, well, down here, which is where we get these bound state models, is when you have got less than that much energy, and that's why we're making only these. That's why if we view the picture backwards, the reason why this bound state can't decay into these 2 particles is because its pole is happening below that threshold. Okay, sort of an unphysical value. But above the threshold, as we crank the energy up, in general you'll come to a place where suddenly, say a 3-particle or 4-particle channel, people say the channel opens. It means you've got enough energy to do that as a physical process. Okay? And then in general, if you looked at the unitarity equations would tell you that a sort of sum, you sort of do these sorts of pictures, and sums over all the possible states you get out, the total amplitude probability has to add up to 1. And there'll be new terms in that sum each time you pass one of these what are called thresholds. And so that means there'll be a series of further branch points hidden along here, corresponding to the opening up of those new processes. Okay? But for these integrable theories, there are no further branch points along there. This should be the only one, because these higher think processes are forbidden by the conservation laws. Okay, so it's a particularly simple picture. Okay, so for general theories, as just said, there'd be further branch points hidden along here, corresponding to places when you can make more particles in your outgoing state. But we've already simplified life by having conservation laws which forbid that from happening. Okay, so this is sort of relatively simple already, but it's not quite as simple as it could be. So the neat thing is that if we transform to the theta variable and consider these amplitudes as a function of theta, using this relation here, okay, theta or theta 1, 2, then something very nice happened, and this is why it was good to use theta rather than anything else, is that these two, so let's label these, maybe this can be C, this can be B, this can be D, and this can be A, okay, the different points on the above and below these two branch cuts. It turns out that in the theta plane, this transformation here sort of undoes those two branch points. Okay, so we have two square root branch points here and here. They both get undone. So this point here, let's call this alpha, goes to the origin, and this branch point here, beta, goes to the point I hide, if you work it out, if I haven't made a mistake. The top of the branch cut goes to the positive real axis in the theta plane, and this goes to B, this goes to D, this goes to A. Okay? So it kind of, you can visualize it pretty much, that this gets opened up, this gets opened up and plonked on top. Okay, so now we had to go twice round here takes us once onto what's an unphysical sheet, and then back onto the physical sheet again. So this whole plane here maps into this what's called, so this is known as the physical sheet, just because it's sort of first direct continuation of physical amplitudes. In terms of theta, this turns into what's called the physical strip. Okay? And in a general theory, if you first of all go around this branch point, well, if you go around this branch point or you go around this branch point, you'll get to different sheets of the Riemann surface of the full function. Okay? So going around this branch point takes us from here down to here. Going around this branch point goes from, well, here up to here. And these are, in general, different sheets. Okay? In particularly simple situations, you only have one other sheet in terms of the S variable. Okay, so you get to the same sheet whether you continue around this point or this point, so that you just think of a two-sheeted cover of the S-plane. And in those cases, there's just a single unphysical strip to pair with the physical strip, and everything is 2πi periodic. Okay, but in general, that's not the case, but you totally eliminate all the branch points by doing this transformation. So then, no branch cuts anymore. Okay? But if we're in a non-integrable theory, of course we could still do this transformation. We'd still eliminate these two branch points, that would be nice, but we'd have further branch points from these higher thresholds, which would still be there. Okay? But in an integrable theory, that's it. Okay? So we've now simplified things, and we're looking for solutions to things like our Yang-Baxter equation and so on, in the set of meromorphic functions on the single value functions on this theta plane. So this is why rapidity is a very nice variable to use. Right. And now you can worry about what things like crossing symmetry and so on do. So crossing symmetry, for example, is the statement that you can look at this amplitude either as a forward channel amplitude this way, or if you view the whole thing with your head on your side, you can think of this as an alternative scattering amplitude in theory, where I sort of swap the little particles I, J, K, L and K. here, if I look at it from the side, I'll sort of take one of these particles to its antiparticle, and my sort of pole will be now across what's called a cross-channel pole. The story gets a bit more complicated, but I'll have to quote these, so we have just some constraints on S of theta. Okay, so once we've simplified life by moving into this theta variable, we can. So this is sort of general nonsense. So S of theta is real for theta purely imaginary. Okay, it's sometimes known as real analyticity. So that's a property you expect on general grounds. And then we have Si, J, Nn of theta, Snn KL minus theta is delta IK delta LJ. That's unitarity. Okay, I won't really justify it here, but basically it's coming from the fact that our sort of chart, once we've got this real analyticity traced back in the S-plane, that means that here the complex conjugate of an amplitude on C is actually the continuation of that same amplitude onto B. Okay, you've got a function which is real along here, and then just a branch cut here. Okay, then S star is exactly the same as S on B. Okay, and if you translate that back into the theta plane, it means instead of saying that S times S star is equal to 1, which is what you'd expect for unitarity, you could say S of theta times S of minus theta is equal to 1, at least along this line here, corresponding to real processes. And then since there are no complex conjugates involved in that equation, you can continue it to the entire theta plane, and it holds everywhere. Okay, so snapshot of why this unitarity equation holds. And then slightly more complicated, you've got Si, J, K, L of theta is equal to Si, L bar, K, J bar of I pi minus theta, and that is a constraint known as the crossing constraint. And basically it's coming from the fact, as I mentioned just now, that every Feynman diagram that you draw in the plane, where you're thinking of time as running sort of from my feet to my head, is the same, is an alternative Feynman diagram for another process where time is instead running from left to right. Okay, and if you kind of do the mapping and figure out what the S, basically it swaps the S and the T variables in the Mandelstam notation. And if you think about what that does to theta, it turns out it corresponds in theta to I pi minus theta here. It corresponds to a continuation of the amplitude from C to A, and in this picture it corresponds to continuing the amplitude like that. Okay. By the way, that's in fact the reason. So this first branch point here is exactly this two-particle threshold I mentioned. That's why there has to be a second branch point and a cut going in the opposite direction, because this corresponds to the cross-channel process. That's a relativistic thing. Okay, so we have those, so those kind of general things, and then we also have the Yang-Baxter equation. I'm afraid you can look in the online notes, and basically you've got to just glue all these indices. You've got to draw, my three-particle scattering process, plugging all these indices together. Okay, and then you'll find the indices sort of join up in two different ways, and that's a non-trivial constraint again. Okay, now the most efficient way is.
Sorry, what's the motivation behind the first constraint?
The real, basically it's coming from it being a pure, well, another way to think about it is it being a pure phase along here. Okay, and so, well, I'd say, being complex conjugates along here. All of these properties are things you can abstract from just looking at individual Feynman diagrams as well. Okay. Yeah, there are, in theories where, for example, parity symmetry is broken, some of these become a little bit more complicated, but I think we just have to accept them as general knowledge at the moment. General nonsense. Okay, so crossing and unitarity, initially you do define them for real theta, and then you can continue them. Actually, the unitarity one is also interesting because I said this relation here, okay, I initially said we should think of theta 1 as being bigger than theta 2, so this corresponds to an in state. Okay, that was how I discussed it at first. But if you suppose that it also works for the other way round, then actually that unitarity relation is just the same as saying we can move these past each other here, and then when we're here, we can use the same relation to move them back again. Okay, and that will spit out another factor of S, and if you sort of work out where all the indices are going, you realise that's exactly the same as the unitarity equation. Okay. And in fact, the Yang-Baxter equation, so that also follows from the Zamenhof-Faddeev algebra, assuming it is, I think the right word is associative. Okay, so the way to think about that is, right, the Yang-Baxter equation is sort of this equality, right? Now say we've got a product of three of these A symbols. So A, I, J, K. So, okay, we want to convert that. So the way to get the S matrix is to convert that from, so here, to start with, I've got rapidities ordered theta 1, theta 2, theta 3 in decreasing order, and I want to rearrange those into symbols in increasing order to figure out what the S matrix should be, because that will then correspond to an out state. And now when I start that process on a three-particle state, I've got a choice. I can first swap these two around, and then do further swaps. Okay, so that corresponds to bracketing like that. Doing the Zamenhof-Faddeev algebra to swap these two, and then these two. Okay? Or I could start A, and bracket it that way, and do the swaps that way. Okay? And if you insist on equality of those two, you get exactly the same Yang-Baxter equation there. Okay, good. So I've had half an hour. And I think I'm going to, so it's better to do a concrete example. So I'll talk about very quickly the Sine-Gordon example to show you a little bit of this machinery in action. And then depending on how much time I've got, I'll try and talk about these bootstrap equations. But this is getting increasingly sketchy, I'm afraid. But with all these indices flying around, it's a little bit hard to see the wood for the trees. So I think it's quite good to see in Sine-Gordon. It sort of simplifies quite a lot, and you can kind of see the technology in action. Get me a chance even to suggest an exercise. Okay, I've chosen Sine-Gordon just because there's a little bit more to get your hands on. So if we're at Sine-Gordon, there'd only be a single particle type, and all this Yang-Baxter stuff would be rather trivial. Okay, we'd have to look for other constraints. Okay, so here I've taken the Lagrangian to be a half d phi squared minus n squared over beta squared. Well, 1 minus cos beta phi is the nice way to normalize everything, because this is a continuation of the Lagrangian I kind of quotes derived in the first lecture. And if you think about what this term looks like, we've got a whole bunch of classical vacua. Okay, so naught, and then 2 pi over beta, 4 pi over beta, and so on. Okay? So it's got infinitely many classical vacua. Phi of x is 2n pi over beta, n an integer. Okay? Now this allows a topological charge, which I'll call Q0, which is, let's normalize it as beta over 2 pi, integral from minus infinity to infinity, dx phi. That's a slightly nerdy way of writing it. But let's write the topological charge as that. Okay, that just gives the suitably normalized total change of the field phi from minus infinity to infinity. Can be non-trivial. Okay, so for Sine-Gordon, we could define a similar thing. It's sort of formally it corresponds to the integral of a locally conserved density still, but it would be trivial because at minus infinity to infinity in the Sine-Gordon theory, the field has to be zero to have have finite total energy. Okay, but here we can have configurations where the field hops between two neighbouring vacua, and for those configurations, Q0 is non-zero. Okay, but it has spin 0, and that's an interesting and relevant fact later. Okay, so the charges that I used to discuss conservation laws before were all higher spin charges, and they also exist in the Sine-Gordon model. But it turns out they're not quite enough to tell all the states apart, and that's going to be crucial. So in order to tell all the one-particle states apart, we have to wheel in this Q0 as well, because all the higher spin charges, apart from at some exceptional points, share the same value for the higher spin charges, and that's going to allow the scattering to be a little bit non-trivial. Okay, so also this higher spin. I won't talk about that. Okay, and so the model has, there exists a soliton, which I'll call S, and anti-soliton S bar with Q0 equals +1 and Q0 equals -1. Okay, and both mass, let's say, capital M. Okay, it's actually kind of non-perturbative, the mass, so but it's, maybe you can work it out, I don't have it from down here. Okay. And these interpolate next neighbouring vacua. Okay, they like interpolate, so the soliton you might consider, say, going from 0 up at -infinity to 2 pi over beta at +infinity. Okay. And there are no stable, classically stable states with higher. No classical stable static solutions with mod Q0 larger than 1. Okay, so if you make a 2-soliton configuration, you certainly can, but it'll turn out that the soliton and the 2 solitons actually repel each other, so even if you start them sitting here, after a while they'll be heading off towards infinity in opposite directions. Okay? There are also some interesting states called breathers. So if you start off with a soliton and an anti-soliton, they'll attract each other, they'll actually sort of oscillate forever. And if I had more time, I'd tell you more about those, but I think I don't have time, so I won't. Right, good. So, what can we say about the quantum theory and the 2 to 2s matrix? I fear I'm not going to say anything about bootstrap equations. I'm not going to have time. Okay, so we expect the higher spin charges survive. Okay, so expect factorized S matrix. Okay, but at generic beta squared, okay, so generic values of the coupling, none of these break the phi to minus phi symmetry of the original Lagrangian. Okay, none break the phi to minus phi symmetry of L. Okay. So none can tell the difference between my soliton and my anti-soliton. Okay? Because the only difference, in fact, between those two is phi to minus phi. Okay. So all that's left is Q0. Okay? And Q0 does tell the difference. Okay? Q0 does break phi to minus phi symmetry, and indeed it's +1 on the soliton and -1 on the anti-soliton. Okay? And on one particle states, it is enough to tell everything apart. Okay, so it resolves the degeneracy we got from just looking at the values of the other charges. But on 2 particle states, that's no longer true. That's what's going to make the S matrix more interesting. So on 2 particle states, it's not going to be able to tell the difference between a soliton and an anti-soliton and an anti-soliton and a soliton. So, but on 2 particle states, it acts as, so if I take Q naught on my possible two-parter, I'll have S, 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 S bar, S bar, S, S bar, S bar. Okay, of course they each have their own rapidities, but because Q0 is of zero spin, Q0 doesn't know about the rapidities, okay? So it can't it's blind to that. So all it knows is that if it sees a net S bar, it measures 2, it measures 0 on those two, it measures -2 on the anti-soliton state. Okay? But Q0 is conserved. So that's enough to tell us that if I start off with SS, I must end up with SS as well. Okay, I've got to keep that conserved. And likewise, if I start off with S bar, I must end up with S bar. But if I've got an S bar, it's not quite enough. It doesn't distinguish the two options for that. Okay, so what I deduce is that if I start off with a soliton-soliton state, then the only thing I can have coming out is another soliton-soliton state. It scatters diagonally. So only into itself. Likewise, S bar, S bar. Okay, but S bar and S bar S can mix without violating any conservation laws. Okay? So for these two, we'll write the amplitude of that. Remember I said we had charge conjugation invariance. It's true in this case too. So I'll write whatever that function is. It's going to be S of theta, which is, if I start off with an S and S, going to an S and S, or S bar, S bar, S bar, S bar. Okay? That will be one function. That's one of the functions I want to know. But for these two guys, I'm going to have, I can have either transmission so I fire a soliton, a faster soliton bumps into a slower anti-soliton, and the soliton remains the faster guy and the anti-soliton remains the slower guy, so I'll call that ST of theta, or reflection. So that would be, although I start off with the soliton being the faster one, after the collision it's the anti-soliton that's the faster one. And I call that SR of theta. Okay, and there's this general sort of motto for these situations that anything which isn't forbidden is compulsory. So you would expect that both of these amplitudes in general be non-zero. If you take the classical limit, then you see classical solitons actually only go through each other, and they kind of can't be a superposition of things. So in the classical limit, you'd expect ST to remain non-trivial, but SR to tend to zero. But away from the classical limit, we're not sure. We'll have to keep those two alive. So now let's get some practice at these wretched Zamenhof-Faddeev algebras, because actually, as I say, advertised it's a kind of handy way for writing everything. So. Let's rewrite that in terms of these little symbols. So AS of theta 1, AS of theta 2 is going to be S of theta times AS of theta 2, AS of theta 1, okay? That encodes the diagonal scattering of two solitons, and we could have the same relation just with S bars everywhere. But then if we start off with AS of theta 1, AS bar of theta 2, that's going to be a linear combination. Okay, there are going to be two options now for my out state. It's going to be ST of theta times AS bar of theta 2, AS of theta 1, plus SR of theta, AS of theta 2, AS bar of theta 1, okay, where theta is equal to theta 1 minus theta 2 in all cases. Okay. So that's, in my previous ways of writing these things down, of course there were these implicit sums on the indices, and this has sort of eliminated all those sums and just written out everything, the only non-zero terms. Okay? And now once you're practiced, this is now the most convenient way to figure out what's going on in terms of what these unitarity and crossing relations are. Because for example, to work out unitarity, all I have to do is realise that I just swap the order of these symbols like this, and then I've still got to swap these two symbols back again, right? And then I'll have the same pair of symbols as I had on the left-hand side, so the coefficient is better be 1, right? So unitarity, these are kind of semi-exercises to check for yourself that you're happy with this. Okay, but when I do the swap backwards, I've now got not theta 1 minus theta 2, but theta 2 minus theta 1. And I'll get another factor of s, but now it'll be s of minus theta. So if you swap these around again, I'll have this factor here, but I'll be pre-multiplied by s of theta times s of minus theta. So unitarity for that one's rather trivial. It's just s of theta, s of minus theta equals 1. Okay, but for this equation it's more complicated because now I swap these two round, and again I generate two terms, and these two back I swap to generate two terms as well. And I want the whole thing, so the whole thing that I get after doing those swaps around is going to be something involving AS of theta 1, AS bar of theta 2. I'll want the coefficient of that to be 1. I'll also get something with AS bar of theta 1, AS of theta 2. I'll want the coefficient of that to be 0 in order to have a proper equality between swapping and then swapping back. So I'll give you two equations now, and they are ST of theta, ST of minus theta, plus SR of theta, SR of minus theta equals 1, and ST of theta, SR of minus theta, plus SR of theta, ST of minus theta equals 0. Okay, so we get to that using these little symbols. Okay, so we're already, it's kind of quite efficient in the sense that we're calculating things. But these can be slight exercises to check. Now crossing, unfortunately I've just rubbed off the key diagrams, but you have to look at all those diagrams I just drew from the side. Okay? And with any luck, you can convince yourself, or ask me to have a go at explaining later, that SR of I pi minus theta should be ST of theta, and S of I pi minus theta is ST of theta. And SR of I pi minus theta is just the same as SR of theta. Okay, so what comes from, it's so handy to draw a soliton, so it's an arrow pointing forwards and an anti-soliton as the corresponding arrow pointing backwards. So for example, this would be the S of theta, and if I look at that from the side, I've now got a soliton here, but now this arrow, since I'm looking at the side, is now an anti-soliton. Okay, but it's scattering diagonally. So that's S being related to ST, whereas if I did it for SR, I'd get the same thing back. Okay, now the hard one, so Yang-Baxter equation. So to get Yang-Baxter, you now have to take, unfortunately, 3 of these symbols in a row and swap them round so that you've oppositely ordered the rapidities in the two possible ways, and then sort of stare at it for a bit. It's not too hard. And you'll get a bunch of equations, which includes, I'm writing this down just to show that it's not totally trivial. So it includes ST of theta SR of theta plus theta primed SR of theta primed plus SR theta S of theta plus theta primed ST of theta primed is equal to SR of theta ST of theta plus theta primed S of theta primed. Okay, so some slightly messy functional equation involving the gadgets we've got, and there's another one involving ST, SR, ST, plus the same indices as before, SR, S, SR is equal to S, SR, S, I think, 2. Okay, with the same arguments as before. Okay, so that's just a matter of hacking through the symbols. Okay, but now we started to get, as I say, we started to get a handle on the whole problem, because we know what, we kind of got enough equations to solve, basically. So, quite sure how much more I'm going to say on this. I'm going to show this much. I only have 10 minutes. So these imply that ST of theta is sinh of lambda theta divided by some lambda. Okay, and it turns out that pi over beta squared is 1 minus beta squared over 8 pi. Okay, you can fix that by various means, and one of the neatest ways to fix it is that you know that for certain values of the coupling there actually pops up an extra conserved charge which forbids this reflection process. Okay, that can be shown, and that then restricts positive value. So that follows, you can there are techniques for fiddling around with these equations. Basically you can set theta or theta prime to 0, and then you can differentiate the equation and also set theta or theta prime equal to 0, and you can just sort of brute force solve these equations to find what the solutions look like. I'd be happy to talk about that with people later if they want, but I think I want to move quickly onto my last mini topic. So that was just to try at least convince you that we can get enough sort of grip on such problems to solve and find the S matrix. So once you've found the S matrix, you then find there's an interesting structure of poles in these S matrix elements, which corresponds precisely to the formation of these breather states that I mentioned that exist in the classical theory. And you can analyze the properties of these things, and you can in some sense solve the model. Of course, from then on, you'd like to go and figure out also other properties of the model, like its behavior in finite volume or correlation functions and all the rest of it. That's a harder task. But I did just very quickly want to mention one further thing, I think, since I've got maybe 10 minutes, so I'll just mention it very briefly. So you can look, there's more on that in these online notes. So all the formulae, if you're upset by these formulae, that they're written properly in the notes that you can find online. I just wanted to very quickly mention one last topic. So what about the situation? So at the moment, the way that I've kind of got a grip on this theory is because there existed this non-trivial Yang-Baxter equation. Okay? Because the soliton and the anti-soliton could get themselves a little bit muddled up in the scattering process, because the only thing that told them apart was the spin zero charge. That meant that I could then write down a non-trivial Yang-Baxter equation, And that helped me to solve the theory, or helped analogical to solve the theory. Okay. But if there is no internal degrees of freedom, like the sort of S bar multiplet we had here, then scattering is diagonal. Is, let's say, completely diagonal. Nothing gets mixed up at all. And the Yang-Baxter equation is trivial. Okay, so the S matrix can be written with only two indices, because we don't need to say what the two outgoing particles are. They're going to be the same as the incoming ones. So we've got Sij of θ1 minus θ2 is just I, j to j, I, with θ1 on that one and θ2 on that one. Okay, we have the simple exchange relation AI of θ1, Aj of θ2 is equal to Sij of θ1 minus θ2, Aj of θ1, Ai of θ2. Okay. And correspondingly, a whole lot of other stuff simplifies. So now my crossing and unitarity equations also simplify. Essentially, because there's less to get mixed up again.
Maybe it's a question, because θ1 and θ2 are changed or not. Maybe have we changed the θ1 and θ2 in this formula or not?
Yes, thank you. Yes. Yep, that was it. Yeah, thanks. That's what you meant, right? Yes. Good. Okay, and then unitarity becomes just Sij of theta, Sij of minus theta equals 1, and crossing just Sij of theta is Sij bar of I pi minus theta. Okay, I'm still allowed to have antiparticles, but I must be able to tell them apart using my conservation laws. And if I take those two equations together, combining, that implies that Sij of theta plus 2 pi I is equal to Sij of theta. So a micro exercise to check that you believe that. Okay? So now we're in the situation where there's only one unphysical sheet. Okay? So remember we had our physical strip here. And then we had these unphysical strips. But now the whole function is 2 pi, this was I pi, that's 2 I pi. Okay, so the whole function is periodic. So in other words, whichever, back in the S-plane, whether I go through the left or the right branch cut, I end up on the same unphysical sheet. Okay? So that means that all amplitudes are simply products of trig functions. Okay, so this makes it somehow an excellent playground. So in the case of the Sine-Gordon model at general values of the coupling, you find a sort of accumulation of poles. When you try and solve, so first of all we've got to solve this Yang-Baxter equation, and in the end we boil it down to this simple, but we still need to figure out what this function S was. Okay, we fixed it up to an overall function S. It turns out if you play around between the unitarity and the crossing relations here, you can derive a sort of iterative solution to figure out what S has to be. And that sort of piles up poles. The further away you go from the physical strip, the more poles you have. And you end up with S being an infinite product of gamma functions. Okay? I mean, it's not the worst thing in the world, but it's quite a mess. Whereas for these cases, okay, because it's 2 pi periodic, actually the S matrix is a very simple product of trig functions. So that makes it kind of a very nice playground for playing around. But of course, the one problem is that we've also lost the Yang-Baxter equation. Okay? So we don't seem to have any sort of foothold on the theories. And now I've got 5 minutes left to explain about 3 papers by Sasha and Analytic, so I'm not going to do that. I'll just draw some pictures, I think, because I'm really... So, in some sense, these theories are very simple. On the other hand, they're also a very good place for sort of exposing some of the elements, structural elements of S matrices, exact S matrices, in ways that are much more obscure. So, although Jean-Sébastien was saying to me yesterday that it'll be years before people completely understand the XXZ model, which in some sense is associated with SU2, there are other features which actually look nicer when you look at models associated with general Lie algebras from the beginning. But the trouble is, of course, if you try and do this for these sort of more complicated models with non-trivial Yang-Baxter equation, you immediately get lost trying to read some wretched article about quantum groups which you don't quite understand, and so on. It becomes very difficult. In these cases, we don't need any of this mess because the Yang-Baxter equation is anyway trivially satisfied. And what Zamolodchikov pointed out, so Yang-Baxter equation is useless here, trivially satisfied, but in about 1989, 1990, Sasha Zamolodchikov, actually his task, he was trying to understand what happened to the Ising model. Okay, so you remember the critical Ising model theory of these little spins that can point up and down, C equals a half. Okay. It was known for a long time that if you change the temperature away from the critical temperature, that model remains exactly solvable. It's relating to 3 fermions and so on. Okay. But nobody knew what happened when you add a magnetic field. Okay, so keep the model at the critical temperature, but add a small magnetic field which favours spins pointing up instead of spins pointing down. Okay, in fact, as a lattice model, written crudely, that's just not integrable. But Zamolodchikov decided to look at this using the techniques of conformal field theory. So taking the CFT at C equal a half and deforming it by adding in the operator corresponding to the magnetic field. Okay? And he had this cunning counting argument, which I mentioned briefly last time, which allowed him to establish that there should be some conserved charges at higher spin. So he had an inkling that the theory was integrable. Okay, that there was an exact S matrix corresponding to this theory. And the question was how to find that S matrix. Actually, curiously, the spins that he found were the first few exponents of the E8 Lie algebra. So that was already a sign there was something clever going on. Okay. But he couldn't use the Yang-Baxter equation because he also, essentially because this was such a simple theory, he expected scattering of these excitations to be diagonal. Okay, so he was trying to posit a diagonal scattering theory, so it was just a bunch of trig functions. He had to just come up with a bunch of trig functions for the excitation. He also didn't know what the excitations were, so what the different masses were again. He was trying to, again, it's all this of pulling yourself up by your bootstraps. So his idea was, well, at least he knew what the first few conservation laws were. Okay? So use the bound state structure instead. So his clever idea was to say that near, say we have, particles I and J in this theory. Say they form a bound state. Okay, so say there's a possibility for 2 of these guys to get together and form a bound state. Then near that bound state, there'll be a pole in the S matrix, and this corresponds to a Feynman diagram with particles ij, and then a particle, say, k bar, travelling forward in time. Okay? And you can think of that. So then here you have to kind of, you have to have a great intuition to how these things work, which is where Zamolodchikov, was extremely cunning. Which is, although strictly speaking, this is happening for unphysical momenta, you pretend it's happening for physical momenta at the moment. If it was happening for physical momenta, these 2 particles could be alternatively considered this long-living bound state particle instead. Okay? So you would expect that if you, given these conservation laws, if you measure a conserved quantity, say Qs, before they collide, the value you get should agree with the value you get if you measure it after they collide. Okay? But the relative rapidities of these guys to form this on-shell bound state, okay, which is the position at which it's long-lived, are fixed. Okay, you can just solve that little relationship for the forward channel momentum that I wrote down earlier. Okay, so this will lead to an equation of the form QSK, okay, or K bar, the value of the conserved charge on that single particle. It's going to be equal to QSI e to the is times, let's say, theta I, plus QSJ e to the is theta j, where theta I and theta j are going to be fixed. Okay, so that's going to give you a non-trivial relationship between between those three conserved charges. Okay, these three numbers characterizing the values of the conserved charges on these three particles. Okay. But of course, if you've got one coupling there, you can have other ones. For example, that I and K can form a J, and so on. So you've got a whole nest of relations between the values of these conserved charges. And it turns out that these relations are very constrained. So in general, there's no non-trivial solutions to these equations apart from all the q's being 0. And remember what I said, that if all these little q's are 0, then the whole conserved charge is 0 because of asymptotic completeness. Okay? So the possible spins for conservation laws in this theory are going to be constrained by the values of S at which this bunch of sort of coupled equations, over-determined set of equations determining these little q's, have simultaneous solutions. Okay, which is rather non-trivial to do. So first of all, he postulated a theory, really almost done now. He postulated a theory just where particle 1 could form a bound state with itself. Okay, and he got a bunch of constraints, okay, which told him that, I'm now going to have to dive for my notes just to remind me. So that gave him that the possible spins were 1, S is 1, 5, 7, 11 and so on. Okay, so he wrote down this constraint which now involves the same Q1 appearing in all three places. Okay? And that was too many because his counting argument had told him there shouldn't be a spin 5. Conserved quantity. So he had to introduce particle 2 as well, so 1, 1, 2. Okay, he thought, well, that might constrain my system a bit more. It turned out, indeed, it did. And in fact, it did exactly right. It killed off that conservation law as well. So then he had enough, and in fact, it also told him the ratio between the masses of particles 1 and 2 had to be given by the golden ratio. And that actually matched what people had found earlier from just numerical work. Okay, they could detect these two particles. But now he had an exact prediction for that ratio, what that ratio should be, which I don't think anyone had guessed before, which was actually given by the golden ratio, which is kind of remarkable. But then when he tries to, there's a similar procedure you can do for the S matrix, and when he tried to make a consistent S matrix, he found he had to add a further bound state particle of particles 1 and 2, let's call it particle 3, to make the whole S matrix consistent. And then he had to deduce S matrices for the other particles, and he carried on going, and he was sort of persistent about this, and he ended up with 8 different particles. Okay, and 8, well, that's the same as E8. So he had sort of seen hints of an E8 structure. And in fact, the system did then close on a spectrum of exactly 8 particles, okay, which actually is coded up very nicely in some geometrical features of the way that the root system for E8 works. And all of that was sort of done by the bare hand, starting with these bootstrap equations. So unfortunately, I'd say if I had another hour, I'd have told you more about this. But I think it's quite a nice thing to explore. And one of the things it does tell you is, so people have subsequently looked at much more complicated models with multiplet structures, which are governed by quantum group symmetries and all these sorts of things, Yangians and so on. And they see signs of the same structure there. But in these models with diagonal scattering, everything is brought into very kind of sharp focus. You've eliminated all the complexity about these sort of non-diagonal scattering and complicated Yang battery equations and all that. And yet there's still some interesting structure to be found. Okay, and that was one of the achievements. So when you hear about E8 in the lab, there was an article, because much more recently some people in Oxford did some experiments where they recreated a sort of thing equivalent to a sort of spin chain, which had the same critical properties as the Ising model. And they found evidence for not only this golden ratio, but also the next mass ratio as well, if I remember right. And they matched this spectrum, which is encoded in the Cartan matrix of E8. So pure mathematicians then got excited. I think he even made the front cover of the AMS, whichever the sort of slightly more popular version of the AMS publications is. So we can say things sometimes that are of interest to pure mathematicians. Anyway, I think I better stop because I'm over time. So.